All right, and now we're looking at learning target number 4. This is identifying types of reactions. We're really looking at 6 types of reactions here, and of course, there are more reactions in those 6, but typically when starting chemistry, these are the 6 that you first learn about. And realize as well, just like everything else, there are usually other names for these, such as the first one, synthesis. If you look elsewhere, you might see that reaction also called combination, and the single displacement, double displacement. Sometimes you'll see that written as single replacement or double replacement, or single exchange or double exchange. So again, don't be confused if you happen to see that. It's really the same thing. One other thing I'll say is that I'm kind of looking back over these screencasts that I'm doing. I'm just doing these as one take because you might realize they do kind of go up to 15 minutes. And so I'm not going to spend hours doing takes and takes, but as I'm doing these, and looking back over it, I'm noticing I say the word a lot. And I've kind of known that for a while, but it really hits you when you go back and look at it again. So I am going to really try to say less. So with that said, let's look at these 6 reactions really quick. And if you look at the learning target, it says knowing the characteristics of these reactions. We're really looking for clues here to try to decide what reaction it is. And I would say 2 of those clues have to do with the general formula. And then in the case of combustion and neutralization especially, it's the products that are formed. So we'll kind of quickly look over these, and hopefully this will give some of you a better idea of how to pick these out. And this is one of these learning targets as well that just really comes down to memorization. There are some learning targets where, like the balance reactions, there's no way to memorize every single reaction. It's just knowing, again, what strategies there are and kind of knowing what you're trying to accomplish. And so you just kind of have to be persistent and keep trying and trying. But the types of reactions, again, there is none of that. It's just recognizing, and that recognition is going to come from memorizing. Most of you are getting it with your notes, but kind of need to commit that to memory now for the test. So let's go ahead then, like I said, look at some of these a little closer. So we start with synthesis, and you can see in red we've got this general equation for synthesis. A plus B is going to form AB. So with synthesis, again, we're getting one product from 2 or more reactants. And you might see it again called combination. So the example used was hydrogen and water. That's a synthesis reaction because we have 2 reactants, hydrogen and oxygen, forming one product, water. Decomposition is basically the opposite. Now we're taking one reactant and breaking it down into 2 or more products. So if we started with some reactant AB, then we're going to get A plus B. We might also have a reactant ABC that's going to decompose into A plus B plus C, and so on. You can kind of see, there's going to be a lot of different ways to look at that decomposition, but that's kind of the general thing of what's happening there. And like it says, there's some clues as well. Decompositions tend to be endothermic, meaning you're going to have to provide energy to keep it going. I tried to show that with the electrolysis of water, but that just wasn't showing up. It was working a little bit, but being able to see that on the overhead, it was not working well enough. So, but that was one thing where I was trying to show you that we've got to supply a constant energy source. In that case, it's electricity. As soon as I stop providing that source of energy, the reaction stops. So there's our first 2, synthesis and decomposition. So really, again, the clues there are just kind of looking at those general equations. And this was one where we watched the video, and kind of a cool video where you've got this reactant, nitrogen triiodide, And it just so happens that this one is actually exothermic. So you might remember the slightest disturbance could be a balloon falling, could be a feather falling. They talk in the video about a mosquito actually landing on it. They're not kidding. I mean, this stuff is just like, they call it a contact explosive. It's just the slightest thing is going to set it off, and it's going to decompose into nitrogen and iodine gases. Again, there's Hofbrinkel, N2, I2, because they're by themselves. So notice, for example, that the reactant also has nitrogen and iodine, but they're not by themselves. So it's not N2I2, it's Ni3, so something different. But you could see this by looking at those puzzle pieces. This is a covalently bonded compound. Got nitrogen with 5 valence electrons, 3 places to bond, iodine with 7 valence electrons, 1 place to bond. So 3 of those iodines are going to take one of those nitrogens. So anyway, just some extra info there. But decomposition, single displacement. Again, we're looking at this general formula. Now, it is a little trickier to see sometimes, but what you're really looking for here is trading places. And you'll notice that we've always have something, in this case we're just going to call it X. X is really switching places from B to A. And one thing that Ace was asking, that kind of comes down to this, what she was asking was, could you have, for example, on the reactant side, Bx plus A? Of course, that does not matter at all, and you'll see that. So realize that, you may have that sometimes where instead of A plus Bx, you have Bx plus A. Doesn't matter, you're just really looking for, trading partners. In this case, X is trading partners from B to A. So that's the key. And this gets into that activity of series of metals, which I'm going to go into in the next learning target. And I know a lot of you are still confused about that. I was hoping by doing the lab, that would be a little more clear. But that lab you did where you had the 6 metals and the copper sulfate, that did not actually work as well as it could have. There were actually a couple problems with that lab. So anyway, again, we're looking for an exchange between that X, whatever that X is, going from B to A. So example here was this. You've got aluminum and iron oxide forming aluminum oxide and iron. So notice that X in this case is oxide. It's the oxygen. The oxygen is actually switching from iron. Get my mouse back here. From iron to aluminum. So if you see that happening where you've got one thing switching from one thing to another thing, think single displacement, because you'll notice that the other reactant and other product, they're just staying one thing. So here you can see that A plus BX formula, and over here BX plus A, or excuse me, it's actually AX plus B. I misspoke there. So again, A plus BX forming AX plus B. That's what I was trying to say. So again, that just comes down to the general equation there. So we'll come back to this later. Single displacement again. Okay, so double displacement, again, the general formula. But notice in this case, the double displacement, we're talking about ionic compounds typically. And in terms of this class, we're just going to stick to ionic compounds. So we have, again, this general equation where we have AB plus CD, and that's going to give us 2 products, AD plus CB. And this order does matter. So you notice before I talked about the reactants, we could call this, instead of AB plus CD, I could say CD plus AB. That doesn't matter. But on the product side, when we see CB, we can't do BC. That's actually, that order does matter. So again, it has to be A first and C first, because A and C, you'll notice from the reactant side, are our first 2 positive ions. Those are both cations. So when we get to the other side, we get the switching going on. There's still going to be the first because they're cations, they're positive ions. So we're going to have B switching from A to C, and D switching from C to A. So that's what's going on there. Again, it's just kind of really looking at an equation and seeing if you can see that format in there. So it takes practice. By no means am I saying that this is easy, but we just got to kind of practice. So I'm going to kind of blow through these to get to the last two here. Combustion, there's not that nice general equation that we had before, but you will see some constants here. So instead of these variables A, B, C, and D, we've got some clues that are going to tell us, if it's combustion or neutralization, these last two. So combustion, you'll see these constants in the reactant. We've always got oxygen. In the products, we've always got carbon dioxide, and we always have water. So when you see those things, that should tell you right away that you've got combustion. It's only one of these that'll pop up in neutralization as well, and that's water. So you'll see water in neutralization as well, which could throw you off. But realize that in combustion, you have these other two. You have carbon dioxide and oxygen. And, it's also exothermic, so we could throw that in there. You guys know from burning things that you can feel heat, you can see light, it's exothermic. So really the only difference between combustion reactions is what are we burning? In this case we're burning methane, but we could replace this CH4 with literally anything. We could replace this with gasoline, which is going to be a pretty complex molecule. Sometimes they'll use octane. You guys might that might sound familiar. When you actually put gas in the car, they talk about the octane rating because within gasoline you have this molecule octane as well. So there's a lot of things in gasoline, and octane is one of those. So again, you can really put pretty much anything here that's going to burn, and you'll have a combustion reaction. And some of you are asking, is this it for combustion? And last year, having taught chemistry, looking into this a little more, there are more reactions that are combustion. Oxygen is not the only thing that something can burn in. But for this class, for physical science, we're going to leave this with oxygen. So again, these are your clues. We've got oxygen on the reactant side, carbon dioxide and water on the product side. And the last one we're going to look at is neutralization, and that's between an acid and a base. And again, I kind of told you guys before, I don't expect you guys to recognize an acid or a base. We did not name acids or bases, so I don't expect you to recognize those. However, there are a couple clues here that you should be able to realize, and one of those is that it's also a double displacement reaction. So we had this in the quiz where one of those choices could end up being two types of reactions, and that was our neutralization. So neutralization is also a double displacement, so look for that AB plus CD equals AD plus CB format. And the other thing you guys can look for is that on the product side we're going to have water. So you can see this is the classic example. We've got hydrochloric acid and sodium hydroxide. So this is a pretty strong acid, given there's other factors as well, like concentration, but hydrochloric acid can be pretty strong. Sodium hydroxide can be a pretty strong base, and if you combine those in the proper ratios, then you will get as products sodium chloride and water. So they call it neutralization because acids have a low pH, bases have a high pH, and when you add them together, you get a pH that's closer to the pH of water, which is 7. So that pretty much rounds it out. Just kind of study those up, and again, check out Chem Fiesta for examples to practice, and hopefully you'll start to recognize these a little more. So that's it for that. 2 more learning targets to go.